Well, welcome back everybody. In this lesson we're going to deal with one of my favorite topics in the course. We're going to explore gear ratios and how gear ratios affect your torque and horsepower. So let's go. So for starters, you've got a couple of gears shown right here on your screen. The little gear has 14 teeth on it. That's the drive gear. That's the one that's providing the power in this case. And the green gear has 28 teeth. It's the one that's receiving the power, so it's being turned by the red one. Um, in an engine, it's pretty obvious where your power source is, but in this little animation, it's not so clear. So my question for you is, how many times is the red gear going to have to turn in order to make the green gear turn around one complete time? Now, I'm willing to bet that you can look at this situation, and if you wanted to, you could stare at it long enough and count how many times the red one has to turn to make the green one turn once. But I'll bet you can look at those gear tooth counts and conclude that in order for the green gear to turn once, 28 teeth are going to have to get pushed through this intersection point. 28 teeth would get the green gear all the way around. And in order for the red gear to turn 28 teeth, it's going to have to turn around 2 times. 2 times 14 will give you 28. So that number, the number of input turns that it takes to get one complete output turn, that is what a gear ratio is. But that's not usually how we determine it. We don't count input turns, we do this. We divide. We count teeth and we divide. When one gear transmits power to another, their relative speeds are determined by the gear ratio. So this is maybe the most important formula in the whole class. To calculate a gear ratio, all we do is divide the number of driven gear teeth by the number of drive gear teeth, or what I like to say is just driven over drive. So in our previous example, there was 28 driven gear teeth divided by 14 drive gear teeth. 28 divided by 14 is a fraction that would be 2, but remember this is a ratio, so we would say that it's 2 to 1. Always remember to put the to 1 on your gear ratios. If it's just 2, that's just a number. That doesn't mean anything. 2 to 1 tells us it's a gear ratio, and we're done. Now for the one shown here, we have a little bit different scenario. Here the drive gear is bigger than the one that's being driven. So the drive gear has 24 teeth on it, but the driven gear only has 12. And you can see that means that the driven gear has to turn a little bit faster. So if we compute the gear ratio of driven over drive in this case, the driven gear has 12 teeth, the drive gear has 24. And so when we compute that, we end up with 12 over 24. That's 1/2 or 0.5 to 1. So we can have gear ratios less than 1 as well. And that means it takes only half of an input turn to get our one complete output turn. And so this is exactly what happens in a drivetrain after the transmission. We've got some sort of a final drive ratio. In this case, it's a ring and pinion. That would be pretty typical on a rear-wheel drive vehicle. And so if our ring gear, which is the big ring being turned, has 43 teeth, but the pinion, that small gear, has 11, what does that gear ratio turn out to be? Well, you take a minute and use your calculator to figure that out. That's a pretty quick question. In this case, the ring gear has 43 teeth. That's the one being driven. The drive gear is the pinion. It has 11. And if you divide that, you get 3.91. But that's not a ratio unless we put to 1 on there. So 3.91 to 1. It takes that pinion gear 3.9 turns to make the ring gear turn once. Now, here's the thing to note. We always round gear ratios to 2 decimal places. And we do that just because that's the standard in the industry. When you read or study or replace a gear ratio, you will always see 2 decimal places on that, and we're going to follow that practice. 2 decimals on gear ratios. Now what that means is that 3 different things can happen when you have a couple of gears meshing and transmitting power. The first thing, and the most common one, is if we have an underdrive. That is to say, if we have a small gear turning a big gear, we have a gear reduction. That is to say, if the driven gear turns slower then our gear ratio is bigger than 1, and we call that a reduction or an underdrive. That's the case here. We had 3.91 to 1. That's definitely an underdrive. We're getting fewer RPMs on our driven gear. Our second possibility is if the gears are the same size. Then our gear ratio is 1 to 1, and we just call that a direct drive. Those two gears will turn the same speed. And the third possibility is if a gear ratio is less than 1, we call that an overdrive transfer or an overdrive gear. It takes less than 1 input turn to get 1 output turn, and therefore our gear ratio is less than 1. And we saw that back here in this example. This turned out to be 0.5 to 1 because we have an overdrive. Our input gear is turning slower than our output gear, which is turning faster. Okay, so with that in mind, how do gear ratios affect torque? Well, very important formula here. Your output torque can always be found, the output side of a gear transfer. All we need to do is take the amount of torque that we put in and multiply it by the gear ratio, and that gives us the amount of torque we get out of a gear transfer. So let's take a look at this problem. How much torque will be present at the rear wheels of this vehicle, that is to say on our drive axles, if the drive shaft turns with 120 foot-pounds of torque? The ring gear here has 43 teeth and the pinion gear has 11. Well, we already showed that our gear ratio here was going to be the driven count of 43 teeth divided by 11 teeth, and we showed just a minute ago that that is 3.91 to 1. Okay, and then our output torque, the amount of torque we get out of that gear on the ring gear, is just going to be the amount of input torque, that would be 120 pound-feet or foot-pounds, times our gear ratio of 3.91 to 1. We get 469.2 foot-pounds, which is why we have a big ring gear, because we get a big torque multiplication, and that helps the vehicle to accelerate. Now, there was a TV commercial a few years ago, you might remember this commercial if you'd seen it, where a stock Toyota Tundra pulls the Space Shuttle Endeavour towards its final display spot in California, and that stock Tundra pulls the Space Shuttle, which weighs over 200 tons, I think it is. Now, the thing to notice here while it's pulling is, are we looking at a lot of torque or a lot of horsepower? It's not going very fast, so the number of horsepower isn't necessarily that high, but it does take a tremendous amount of torque to do that kind of pulling. And how are we getting that torque? The engine in the Tundra doesn't have to be that powerful, but with adequate gears, the rear wheels can pull with the amount of torque that they need. So this commercial is really much more of a display of the torque that the Toyota Tundra could produce rather than the horsepower. If we were trying to pull that shuttle over the bridge in a hurry, then we'd be dealing with horsepower, but this is purely torque on display here. And also, the Tundra, I'm sure, is a great truck, but any four-wheel drive truck with a low range on a transfer case could probably do the job. The key is to have very low gearing, and most four-wheel drive trucks have low enough gearing to accomplish that. So here's our third formula. Output RPM can also be found. All we need to take is our input RPM, but this time we divide by our gear ratio. So the output gear will turn whatever the input gear is turning when you divide by the gear ratio. So let's look at this example. How fast will the rear wheels turn if the drive shaft, that is to say our input power, is turning at 2200 RPM? Well, let's use our formula here. Our output RPM is our input RPM, 2200 RPM. But this time we don't multiply, be careful of that. We're going to divide by our gear ratio. So we're going to divide by 3.91. We're using the same gear set. And when you divide by that 3.91 gear ratio, you get about 563 RPMs. So the key is, those rear wheels are turning with a lot more torque than they started with, but they're also turning a lot slower than they were, than the drive shaft was. So our torque goes up, but our RPMs go down. Okay, well, what about gears that are working together? We call these tandem gears. Here's a set of tandem gears. The red turns the blue is connected to the yellow, and the yellow turns the green. So we have one gear transfer immediately feeding another gear transfer. What's the math that's going on here? Well, this breaks down pretty easily. First of all, we have the red turning the blue, or in other words, a 14 turning a 24. So if we take the driven over drive here, our gear ratio for red turning blue is driven over drive. That's going to be 24 driven by 14. And that gear ratio turns out to be 1.71 to 1. But the blue gear, which is directly attached to the yellow, then turns the green. So in our second gear transfer, we have driven of 28 being turned by a drive gear of 14. That yellow might be a little bit hard to see. I'm going to make that nice and dark. And when you divide those two out, 28 over 14, that one's pretty easy. That turns out to be a 2 to 1 gear ratio. Or if you wanted to put 2.00 to 1, that would be fine. So how does the red turning blue and green turning yellow interact? Well, we multiply them. Gear ratios that are working together get multiplied. And so in this case, we're going to take 1.71 and multiply it by 2, and that means our total gear ratio for this entire system is 3.42 to 1. Now there's no formula associated with that. That's just a mechanical fact that you need to know. When one gear set works right alongside another gear set, we multiply them to get their overall gear ratio. And that's exactly what happens in your automotive transmission. Whether it's an automatic or a manual, there's lots of gears in tandem. Manual transmission's a little bit easier to follow because the power comes in, the power gets transferred to the counter shaft, and then depending on what gear you're in, the power gets transferred back to the output shaft. So there's usually at least 2 gears in tandem inside a manual transmission. Automatics often have more than that. So here's a cutaway view of what happens in a manual transmission. We have an input shaft which is attached to the engine, and the power comes in to that first green gear. That's a 20-tooth gear. That gear turns the gear below it, this 24-tooth gear, and so the power then goes to this bottom shaft of gears, which is called the counter shaft. Now at that point we've had one gear transfer. That 20 is turning a 24. So in other words, the 24 is driven and the 20 is the drive. So we can figure out what that gear ratio is. That gear ratio is going to be 24 is driven over drive, which is 20, which turns out to be a 1.2 to 1 gear ratio for this first gear transfer right here. Well, now the counter shaft is turning, and so when you shift your manual transmission, we're always choosing which gear takes power off the counter shaft. We're looking for second gear here, and so right here, this is the pair of gears that's used in second gear. So that means our power is going to come right back up. This 15-tooth gear is going to turn that 27-tooth gear, and that then sends the power out of the transmission. All these other gears are just spinning. They're not actually transmitting any power. So for this second gear transfer, the 15-tooth gear is the drive gear, and the 27-tooth gear is the one that's driven. So this time we have 27 driven by a 15. 27 driven by 15 or divided by 15 turns out to be 1.8 to 1, and that's the gear ratio for our second gear transfer. Now, as we just saw, when we have gears working together, we multiply those, and 1.2 times 1.8 turns out to be 2.16, and that is the overall gear ratio then for second gear, 2.16 to 1, and we're done. That means the engine has to turn 2.16 times to get the output shaft of the transmission to turn once. Okay, I'd like you to give this one a try. This is the same transmission, but we've shifted into fifth gear now. It's an overdrive gear. Um, I'd like you to figure out what the gear ratio is for fifth gear in the transmission shown. Unpause your video when you're ready to see the solution. Okay, so our engine power comes into the top green shaft here and goes down to the counter shaft in just the same way. There's no difference at all from any gear in the transmission at that point. This is still 24 driven by a 20. That gear transfer is the same for every one of our transmission gears, and that was 1.2 to 1. The difference is when we shift into fifth gear, we're not going to use this gear set marked 2, we're going to use the gear pairing marked 5. So our power is going to go all the way over to this gear pair right here where the 28 turns the 18 and then it goes out of the transmission. So our power flow is going in and down to the counter shaft but then back up to the output shaft. So 28 is our drive gear for this second pairing, whereas the 18 is our driven. And so when we put driven over drive, that becomes 18 over 28 for our second gear pair, which is 0.64 to 1. Now that we know that our first gear pair is 1.2 to 1 and our second gear pair is 0.64 to 1, we can now multiply those together to get our transmission gear. And that turns out to be 0.77 to 1. And since that's less than 1, that confirms that this is definitely an overdrive gear, which is what we'd expect for fifth gear in a manual transmission. If you didn't get 0.77 to 1, go back and watch that again and see if you can spot what went wrong. Okay, well, that leads us to our last main idea here. When we talk about the overall drive ratio of a gear set or of an entire drivetrain, that means that we're taking the transmission and the final drive, the differential, as the case may be, or the ring and pinion on the drive axle. We're taking all those gears and we're going to combine them into a single ratio. And so the math there is really easy. All we need to do is multiply those. So for example, in third gear of a transmission, we have a ratio of 1.34 to 1, calculated just like the problems we just did. Our rear axle ratio is 2.73 to 1. And so the overall drive ratio for this transmission turns out to be 3.66 to 1. That's our overall drive ratio. That means the engine has to turn 3.66 times in order to make the drive wheels turn once. And that leads us to our last problem. And this is maybe one of the most important ideas of this lesson. We've got an engine here that's creating 125 foot-pounds of torque at 3,000 RPM. We want to figure out how much torque is present at the rear wheels and how fast they're rotating. So let's start out with torque. We know that the engine is generating 125 foot-pounds of torque. Let's start with that. Now we just showed in a moment ago that the overall drive ratio for a 1.34 third gear and 2.73 to 1, we multiplied those, and this turned out to be a 3.66 to 1 overall drive ratio. So to figure out our output torque, that is to say the rear wheel torque, we take our input torque of 125 foot-pounds according to the formula that we had before and multiply it by our gear ratio of 3.66 to 1. And that turns out to be 457.5, and those are now foot-pounds. Now for our output RPM, I'll do that in a different color here. To find our output RPM, we're just going to take our input RPM, which we know the engine is turning at 3,000 RPMs, and we're going to divide that by our gear ratio of 3.66. And that turns out to be 819.6. You could certainly call that 820 RPM. And we're done. So the thing I want you to notice here is because of our third gear and our overall drive ratio of 3.66, our torque went up from 125 up to 457, but our RPMs went down. We made a trade-off there, and that's what gears do. But here's the important fact. How much horsepower is available at the engine and at the rear wheels? That's going to require one more calculation. So let's take a look up here at our engine. We had 125 foot-pounds at 3,000 RPM. We know from our earlier work that horsepower is found by taking the torque times the RPM and dividing it by 5252. So if you do that, you end up with 71.4 horsepower at the engine. Okay, and that takes care of that. But now let's do that calculation again at the rear wheels. Our horsepower back here is also found by taking the torque times RPM and dividing it by 52. But our torque is 457.5. Our RPMs are 819.6, and we'll divide that by 52. If you perform that calculation, you get 71.4 horsepower. So what can you conclude about the drivetrain on that horsepower? It doesn't change. That's an important fact. Horsepower stays the same as we go through gear ratios, even though the torque and the RPMs will change. So when we saw that Toyota Tundra pulling the space shuttle, we had a large gear factor in there that was increasing our torque dramatically, which allowed us to pull the space shuttle. But we couldn't do it very fast because no matter what gears we use, we're not changing the amount of horsepower. We're not changing how fast that work can be done. Okay, so that wraps up this really important topic, but there's a number of key facts that I want to make sure that you recognize and remember from this lesson. The first one is gear ratio. Gear ratios are always calculated by just dividing the number of driven gear teeth by the number of drive gear teeth. The second important fact is that if we want to find the amount of torque we get out of a gear set, we just take the torque that we put in and multiply it by the gear ratio. But if we're talking about speed, the output speed or RPM will always be the input RPMs divide by the gear ratio. Make sure you divide when you're calculating your output RPM. When we have gear ratios in tandem, we multiply the individual gear ratios together to find the overall gear ratio. And even though we have formulas that calculate the output torque and output RPM, there is no formula for output horsepower because the output horsepower is always the same as your input horsepower. Gear ratios have no effect and do not change the amount of horsepower being transferred in a gear system. Okay, those are important concepts. You're going to have some practice problems. Make sure to let me know if you have trouble with any of those practice problems. And we're going to continue using these mechanical concepts in our next lesson. We'll see you then.